September 15th, 1898. Bethlehem Steel Company, Pennsylvania. The European-trained metallurgists watching Frederick Taylor's experiment that morning were certain they were about to witness catastrophic failure. American steel cutters heating tool metal to temperatures that defied every principle Sheffield's Royal Institute had established for 70 years. Through the smoke and sparks of the Pennsylvania machine shop, Taylor pushed his cutting tools beyond the absolute limit, 1600 degrees Fahrenheit. No higher, European doctrine demanded. Above that temperature, grain growth destroys steel. Tools become brittle. Cutting edges fail instantly. For 3 decades, every machine shop from Pittsburgh to Chicago had accepted the same brutal mathematics: 30 surface feet per minute maximum cutting speed, or watch your tools lose their temper and go soft. European experts had proven this limitation was absolute, unbreakable, yet Taylor was heating his experimental steel to 2100 degrees, red-hot temperatures that should have destroyed the metal's structure completely. The European observers expected immediate, spectacular failure when that glowing tool touched hardened iron. Instead, something happened that contradicted everything the metallurgical world believed possible about the relationship between heat and steel cutting performance. The mathematics were unforgiving. Frederick Winslow Taylor stood in Bethlehem Steel's cavernous machine shop on that April morning in 1898, watching the same scene that had frustrated American manufacturers for decades. 30 surface feet per minute, not 31, not 29 3/4. Exactly 30 feet per minute was the absolute ceiling for cutting steel, and every machinist in America knew what happened when you pushed beyond it. The cutting tool would heat up, lose its temper, and go soft as butter. The edge would dull, the workpiece would tear instead of cutting clean, and 8 hours later you'd have one finished locomotive drive wheel instead of the 3 that American industry desperately needed. Taylor pulled out his pocket watch and confirmed what the production sheets already told him. Bethlehem's massive machine shop was running at full capacity, but orders were backing up faster than the lathes could turn. Company president Robert Lindeman had been brutally direct during their meeting the previous week. "Find a way to cut steel faster, Taylor, or we build another shop." The economics were simple enough. Each new machine shop cost $200,000 and took 18 months to construct. Every day of delayed orders meant Carnegie Steel and other competitors were capturing Bethlehem's customers. American industrial appetite was growing faster than American machines could feed it, and the bottleneck was always the same: that 30-foot ceiling. The established wisdom came directly from Sheffield, England, where Robert Mouchet had published his definitive formula in 1868: heat tool steel to 1400 degrees Fahrenheit, no higher. Above 1600 degrees, you get grain growth, brittleness, failure, the Royal Institute of Metallurgy had declared. European-trained engineers at Carnegie Steel, Midvale Works, and Bethlehem itself nodded in agreement whenever the subject arose. The science was settled. The limitations were absolute. But Taylor had already noticed something the Europeans missed. During his decade at Midvale Steel Works, he developed the habit of timing everything with a stopwatch, measuring every operation down to the second. While doing these time studies, he'd watch the best machinists work differently than the textbooks taught. They let their tools heat up during heavy cuts, not red hot, but warmer than conventional wisdom allowed. They kept cutting when others stopped to let tools cool, and somehow their finished work came out better, not worse. The contradiction nagged at Taylor with the persistence of an engineer who'd built his reputation on systematic observation. If European metallurgical science was correct, these experienced machinists should be ruining their tools and producing inferior work. Instead, they were the most productive operators in the shop. Either decades of scientific research were wrong, or the best craftsmen in America didn't understand their own trade. Taylor convinced Lindeman to let him experiment. The company allocated $5,000 and assigned metallurgist Maunsel White III to work with him. White was a practical man who understood both the chemistry of steel and the realities of production schedules. Together they started with Mouchet's standard formula: 2% carbon, 2.5% manganese, 7% tungsten. Their first tests in May showed promise. Heating to 1500 degrees produced tools that cut slightly faster than standard ones. Then Taylor made the decision that would either revolutionize American manufacturing or end his career. He pushed the temperature to 1700 degrees Fahrenheit, 300 degrees beyond what any European authority considered safe. The results were catastrophic. The steel became so brittle it chipped on first contact with the workpiece. The tools were useless, Taylor wrote in his notebook that evening. Every expert in the country would say I told you so. Word of the failure leaked beyond Bethlehem's walls with the speed that bad news travels in tight industrial circles. Letters arrived from professors at Stevens Institute and MIT warning that Taylor was pursuing a metallurgical dead end and wasting Bethlehem's capital on impossible theories. The American Society of Mechanical Engineers buzzed with speculation about whether the efficiency expert who'd revolutionized time studies and scientific management was finally reaching beyond his competence. The criticism stung because it touched Taylor's deepest professional insecurity. Born into Philadelphia society with a Harvard acceptance in hand, he'd chosen instead to work as an apprentice machinist, learning American manufacturing from the shop floor up. He believed passionately that systematic experimentation could overcome any limitation, that American industrial methods could surpass European tradition through superior measurement and analysis. But if Frederick Taylor, who'd already proven that scientific management could transform factory productivity, couldn't solve this basic metallurgical problem, what did that say about American innovation versus European expertise? The technical challenge was matched by a personal one. Taylor's reputation as the apostle of scientific management rested on his ability to find systematic solutions to industrial problems. Time and motion studies had proven that workers could be more productive when their methods were scientifically analyzed and optimized. But steel metallurgy operated by different rules than human efficiency. You couldn't time study your way past the fundamental chemistry of how carbon and tungsten behaved under extreme heat. Standing in that machine shop in late May, watching another batch of experimental tools fail catastrophically, Taylor faced the possibility that some limitations were genuinely absolute. European metallurgical science might be correct. 30 surface feet per minute might represent the true physical ceiling of what cutting tools could achieve. The mathematics that govern steel chemistry might be more fundamental than the mathematics he'd used to optimize human productivity. Yet something in Taylor's engineering mind refused to accept defeat. The best machinists still worked their tools hotter than the textbooks recommended, and their results still contradicted European theory. If systematic observation had revealed inefficiencies in human work patterns, perhaps it could reveal inefficiencies in metallurgical assumptions as well. The question wasn't whether European science was wrong, but whether American experimentation could discover what European science had missed. Taylor's response to the May failures was characteristically American: more experiments, better data, and systematic documentation of everything. He and White established a research program that would consume 26 years and cost Bethlehem Steel $200,000, equivalent to $6 million in modern currency. They would test every variable that might affect steel performance: temperature, cooling rate, chemical composition, timing, and dozens of factors that European metallurgists had never considered worth measuring. The scale was unprecedented in American industrial research. Each day brought 20 to 30 test batches through Bethlehem's experimental furnaces. Each batch required precise temperature measurement using pyrometers, new technology that cost $500 per unit. Taylor installed 6 of them throughout the metallurgy shop, creating the most sophisticated steel testing laboratory in America. White modified the steel composition weekly, sometimes daily: more tungsten, less carbon, add chromium, adjust manganese by fractions of a percent. The numbers from the summer of 1898 revealed the magnitude of their systematic approach: 400 to 500 recorded experiments per month. 3,000 pounds of steel consumed monthly in testing. Temperature ranges from 1,200 degrees Fahrenheit to 2,300 degrees, far beyond what any previous researcher had attempted. The failure rate remained brutal. 85% of all tests produced steel that was either too brittle, too soft, or chemically unstable. White's laboratory notebooks from this period read like a metallurgical exploration of uncharted territory. Batch number 217, tungsten increased to 8%, heating to 1900 degrees, air cooling. Result, excessive grain growth, brittle failure. Batch number 218, same composition, furnace cooling instead of air cooling. Result, acceptable hardness, edge retention, poor. Each entry represented hours of preparation, careful temperature control, and detailed analysis of the failed results. The breakthrough moment came in September 1898, not from planned experimentation, but from what appeared to be operator error. White was supervising a routine test batch when the furnace operator accidentally overheated the steel to 2100 degrees Fahrenheit. According to European metallurgical doctrine, this should have produced completely worthless metal with catastrophic grain growth and brittleness. White was prepared to discard the batch when Taylor arrived and insisted on testing it anyway. The ruined steel behaved unlike anything they had seen. When cooled slowly in air rather than quenched in water, it didn't crack or show the brittleness that European theory predicted. Instead, it displayed a strange stability that contradicted fundamental assumptions about how extreme heat affected steel structure. Taylor immediately ordered systematic testing of the accidentally overheated batch, and the results challenged everything the metallurgical world believed about the relationship between temperature and steel properties. The accidental discovery revealed that European limitations weren't based on complete understanding of steel behavior under extreme conditions. Sheffield's research had established safe operating parameters for conventional steel working, but had never explored what happened when those parameters were deliberately exceeded by massive margins. The Europeans had been correct within their testing range, but their testing range had been artificially constrained by assumptions about what temperatures were worth investigating. Taylor realized he was exploring metallurgical territory that had never been systematically mapped. European researchers had focused on optimizing steel within known limitations rather than discovering whether those limitations were fundamental or merely conventional. American industrial pressure for higher productivity had driven him into temperature ranges that European craftsmen had never needed to consider, because European manufacturing operated at lower production speeds with different economic constraints. Through the fall of 1898, Taylor and White methodically explored the high-temperature region that the accidental overheating had revealed. They discovered that steel behavior above 1900 degrees followed different rules than steel behavior in the conventional range. The grain growth that European metallurgists feared actually stabilized at extreme temperatures, creating microstructures that were impossible to achieve through conventional heat treatment. The systematic documentation became crucial as their experiments moved further from established metallurgical knowledge. Each test required precise recording not just of temperature and composition, but of heating rates, cooling methods, furnace atmosphere, and timing. Variables that seemed insignificant in conventional steel working proved critical when operating at temperatures that European science had declared impossible. By December 1898, their experimental program was consuming nearly Bethlehem's entire research budget. Lindemann demanded progress reports that Taylor struggled to provide in terms that business leadership could understand. The technical discoveries were promising, but translating metallurgical breakthroughs into production improvements required additional months of testing to develop practical applications. White's role became increasingly important as the experiments moved beyond Taylor's mechanical engineering expertise into pure metallurgical chemistry. The interaction between tungsten, carbon, and extreme heat followed principles that required deep understanding of atomic structure and chemical bonding. White's third-generation metallurgical knowledge provided the theoretical foundation that made sense of their experimental observations. The winter months of 1898 into 1899 established the pattern that would define their research for years to come. Systematic experimentation guided by careful measurement, combined with willingness to test conditions that European authority had declared impossible or dangerous. Each failure provided data that refined their understanding of how steel behaved under extreme conditions. Each success opened new questions about why conventional limitations had been accepted without thorough investigation. Taylor's engineering mind thrived on the systematic nature of the challenge. Unlike optimizing human productivity, where workers might resist change or provide inconsistent performance, steel chemistry followed, discoverable laws that could be measured and replicated. The question was whether American industrial research could invest sufficient time and resources to map the metallurgical territory that European science had left unexplored. By September 1899, Taylor and White had discovered the metallurgical secret that would transform American manufacturing. At temperatures near steel's melting point, tungsten dissolved completely into the metal's atomic structure, creating what Taylor called red hardness. This was the opposite of everything European metallurgy taught. Instead of becoming softer as temperature increased, their experimental steel actually became harder when heated to glowing red temperatures during cutting operations. The mechanism was revolutionary and contradicted fundamental assumptions about how steel behaved under extreme heat. Traditional carbon steel lost hardness above 1,000 degrees Fahrenheit because its internal structure broke down as temperature rose. The carbon atoms that provided hardness became mobile and migrated away from the cutting edge, leaving soft, useless metal. European metallurgists had spent decades optimizing steel compositions to delay this inevitable softening, but had never imagined that the process could be reversed. Taylor's extreme heat treatment locked tungsten atoms into the steel matrix so tightly that they actually strengthened the metal as temperatures rose during cutting. The tungsten formed carbide compounds that became more stable under heat stress, not less. The hotter the tool got during operation, the harder the cutting edge became. This inverted the fundamental relationship between heat and tool performance that had limited every machine shop in America. White's chemical analysis revealed the precise mechanism during late fall experiments. At 2100 degrees Fahrenheit, tungsten carbides formed complex molecular structures that were impossible to create at lower temperatures. These structures acted like microscopic reinforcement throughout the steel matrix, becoming more effective as operational temperatures increased. European metallurgists had never discovered this because their research had never systematically explored the high-temperature region where tungsten carbide formation occurred. The first successful cutting test took place on March 15, 1900. Taylor personally operated the lathe while White monitored temperatures, and Lindemann watched from across the machine shop. The Taylor-White steel tool, glowing cherry red from cutting heat, maintained its sharp edge for 3 continuous hours while cutting at 90 surface feet per minute. This was triple the speed of the fastest conventional tool in America, achieved while the cutting edge glowed bright enough to read by. The visual spectacle was as impressive as the technical achievement. Metal chips came off the workpiece bright blue from the extreme heat generated by the unprecedented cutting speed. The chips were too hot to touch and had to be cleared away with long-handled tools. Yet the workpiece itself remained cool enough to handle with bare hands, because the Taylor-White steel was cutting so efficiently that heat was carried away in the chips rather than conducted into the work. Taylor's notebook entry that evening captured his amazement at witnessing metallurgical principles turned upside down. The lathe operator was frightened by the red glow and burning chips. He had never seen metal cut this way. Neither had anyone else in America or Europe. The demonstration had achieved cutting speeds that violated every limitation the machine tool industry had accepted as fundamental physical law. Word of the March test spread through Bethlehem's engineering department with the speed of truly revolutionary discovery. Machinists gathered around the experimental lathe to witness subsequent demonstrations, watching steel cut at speeds that seemed to violate basic physics. The glowing tool maintained perfect geometry while removing metal faster than any cutting operation they had witnessed. Production calculations that had governed machine shop economics for decades became obsolete overnight. White's metallurgical analysis confirmed that they had discovered an entirely new category of steel behavior. The tungsten carbide structures that formed under extreme heat treatment created what he termed inverse thermal response. Unlike conventional steel that weakened under heat stress, Taylor-White steel strengthened as cutting temperatures increased. The harder you worked it, the better it performed. The implications for American manufacturing were staggering. Machine shops operating at Taylor-White speeds could produce 3 times their current output without adding equipment or floor space. The locomotive drive wheels that required 8 hours using conventional tools could be completed in less than 3 hours. Bethlehem's production bottlenecks could be eliminated without building new facilities or hiring additional workers. Taylor immediately began scaling up production of the experimental steel. White designed furnaces capable of achieving the precise temperature control required for 2100-degree heat treatment. The process demanded careful attention to heating rates, atmospheric conditions, and cooling procedures that were far more complex than conventional steel working. Any variation in the thermal cycle could produce brittle failure instead of red hardness. The manufacturing challenges were significant but solvable. Each batch of Taylor white steel required individual attention from skilled furnace operators who could judge temperature by color and adjust heating cycles based on furnace behavior. The pyrometer technology that enabled precise measurement was expensive but available. The tungsten required for the steel composition was more costly than conventional alloying elements, but represented a small fraction of the productivity gains the new steel enabled. By summer 1900, Taylor was confident he had solved the fundamental limitation that constrained American manufacturing productivity. Bethlehem's main machine shop began converting its operations to take advantage of Taylor white steel capabilities. Line shaft speeds increased from 90 revolutions per minute to 250. Production schedules were rewritten to reflect the tripled cutting speeds. Orders that had been backing up for months could suddenly be completed on schedule. The success attracted attention from throughout American industry. Representatives from Carnegie Steel, Baldwin Locomotive, and other major manufacturers visited Bethlehem to observe the revolutionary cutting demonstrations. Taylor began preparing technical papers for the American Society of Mechanical Engineers describing the metallurgical principles behind red hardness. Patent applications were filed covering both the steel composition and the heat treatment process. Yet, beneath the excitement over breakthrough performance, White harbored concerns about the steel's behavior under different operating conditions. Laboratory tests had focused on continuous cutting operations where the tool remained engaged with the workpiece. Real production involved interrupted cutting, vibration, and shock loads that their systematic testing had not yet thoroughly explored. The tungsten carbide structures that provided red hardness might behave differently under the complex stress patterns of actual manufacturing operations. Success bred dangerous overconfidence through the spring and summer of 1900. Taylor became convinced that his metallurgical breakthrough had permanently solved American manufacturing's greatest bottleneck. Bethlehem Steel's main machine shop underwent wholesale conversion to exploit Taylor white steel capabilities. Production schedules that had seemed impossible in March became routine by June. Orders poured in from customers who had heard rumors about Bethlehem's revolutionary cutting speeds. Lindemann authorized major capital investments based on Taylor's projections. New lathes designed specifically for high-speed operations were ordered from Cincinnati Milling Machine Company. The machine shop's line shaft system was rebuilt to handle sustained operations at 250 revolutions per minute instead of the traditional 90. Bethlehem's sales department began accepting contracts with delivery schedules that would have been impossible using conventional cutting tools. The euphoria extended beyond Bethlehem's walls. Taylor presented preliminary findings to the American Society of Mechanical Engineers in May, describing red hardness as the solution to limitations that had constrained American industrial growth. Engineering journals published enthusiastic articles about the potential for tripling manufacturing productivity without building additional facilities. Investment bankers began calculating the economic impact of applying Taylor white steel throughout American heavy industry. Yet White's private concerns grew as production applications revealed complexities that laboratory testing had not anticipated. The controlled conditions of experimental cutting differed significantly from the harsh realities of production operations. Real manufacturing involved interrupted cuts, where tools were repeatedly slammed into and out of the workpiece, creating shock loads that their systematic testing had never thoroughly explored. The catastrophic failure that nearly destroyed everything occurred on August 15, 1900, during a demonstration for potential investors from Pittsburgh and Chicago. Taylor had arranged the event to showcase Bethlehem's revolutionary capabilities before an audience that included executives from competing steel companies and representatives from major manufacturing customers. The demonstration began flawlessly. A Taylor white tool cutting hardened steel at unprecedented speed, while glowing cherry red producing the spectacular shower of blue-hot chips that had become the signature of high-speed steel operations. The investors watched in fascination as metal peeled away at rates they had never imagined possible. For 45 minutes, the cutting proceeded exactly as Taylor's presentations had promised. Then the tool shattered without warning. The failure was not gradual dulling or edge wear, but sudden, catastrophic destruction that sent carbide hard fragments scattering across the machine shop floor. The sound was explosive, like a rifle shot echoing through the high-ceilinged space. Workers dove for cover as metal shards ricocheted off machinery and walls. The silence that followed was devastating. Investors who had been taking notes on revolutionary cutting speeds were now staring at a broken lathe and scattered debris. Taylor stood beside the machine, his face pale, realizing that his moment of triumph had become a public demonstration of dangerous unpredictability. White's immediate failure analysis revealed the problem that would haunt high-speed steel development for years. The tungsten carbide structures that provided red hardness under continuous cutting were vulnerable to shock and vibration under interrupted cutting conditions. When the tool repeatedly engaged and disengaged the workpiece, stress patterns developed that could cause catastrophic fracture with no advance warning. The technical explanation was clear, but professionally devastating. Taylor's steel was not simply an improved version of conventional cutting tools. It was a completely different category of cutting implement that required different operating conditions, different machine setups, and different applications. The breakthrough that promised to revolutionize all manufacturing could only be applied safely to specific types of cutting operations. Industry response was swift and brutal. The American Machinist published an editorial titled "The Danger of American Overconfidence," warning that Taylor's experimentation represented dangerous innovation that prioritizes speed over safety. Carnegie Steel's chief metallurgist publicly called the Taylor-White process reckless experimentation that could injure workers and destroy expensive machinery. Professional criticism cut deeper than public ridicule. Colleagues who had initially supported Taylor's research began questioning whether his systematic approach had been thorough enough. The August failure suggested that laboratory testing, no matter how extensive, might not reveal all the ways that revolutionary materials could fail under real operating conditions. White found himself defending not just the steel's technical merits, but the entire philosophy of pushing beyond established limitations. European-trained metallurgists pointed to the August disaster as proof that American industrial ambition led to dangerous shortcuts in engineering safety. The failure validated conservative approaches that emphasize proven performance over breakthrough capabilities. Yet Taylor refused to interpret the August setback as fundamental invalidation of his approach. His engineering mind focused on understanding exactly why the failure had occurred and what operating conditions would prevent similar catastrophes. The tool had not failed because red hardness was impossible, but because it had been applied inappropriately to cutting operations that exceeded its design parameters. Working with Norwegian mathematician Karl Barth, Taylor began developing precise operating guidelines that would define safe applications for high-speed steel. Continuous cuts at sustained high speed, rigid machine setups to minimize vibration, specific feed rates that maintained constant tool engagement. Most importantly, they recognized that Taylor-White steel excelled in applications where heat was the limiting factor, not in operations where shock resistance was paramount. The failure analysis transformed Taylor's understanding of what he had discovered. High-speed steel was not a universal solution to manufacturing limitations, but a specialized tool for overcoming specific bottlenecks where conventional cutting failed due to heat buildup. Applied correctly, it could revolutionize certain types of production. Applied incorrectly, it could be more dangerous than conventional tools. By October 1900, Taylor had learned the most important lesson of his metallurgical research. Breakthrough innovation required not just discovering new capabilities, but understanding their appropriate limitations. The August failure had been professionally embarrassing but technically valuable. It defined the boundaries within which red hardness could transform manufacturing and beyond which it became hazardous experimentation. The path forward required rebuilding credibility through systematic demonstration of controlled applications rather than dramatic claims about universal revolution. Taylor's steel had not failed as metallurgical innovation. It had failed as carelessly applied technology that promised more than it could safely deliver under all operating conditions. Taylor's response to the August disaster was methodical analysis rather than retreat. Through the fall of 1900, he and White systematically identified the precise conditions where their steel excelled and where it failed catastrophically. The breakthrough was not brittleness resistance, they realized, but heat resistance. The tool was not meant to replace all cutting applications, but to revolutionize operations where heat buildup had always been the limiting factor. Working with Norwegian mathematician Karl Barth, Taylor developed operating guidelines that transformed high-speed steel from dangerous experimentation into controlled technology. Continuous cuts at sustained high speed, rigid machine setups that eliminated vibration, specific feed rates that maintained constant tool engagement with the workpiece. Most importantly, they determined that Taylor-White steel excelled where conventional tools failed from heat buildup, not where shock resistance was paramount. Barth's mathematical precision proved crucial for translating metallurgical discovery into practical manufacturing procedures. His slide rule calculations determined exact combinations of cutting speed, feed rate, and depth of cut that would maintain the continuous engagement necessary for safe high-speed steel operation. Each application required careful analysis to ensure operating conditions matched the steel's capabilities rather than exceeding its limitations. The rehabilitation process was slow and methodical. Instead of dramatic demonstrations before large audiences, Taylor arranged private sessions with individual engineers who could observe controlled cutting operations under ideal conditions. Each demonstration was carefully planned to showcase applications where high-speed steel provided clear advantages without risking the spectacular failures that had damaged his credibility. By March 1901, Taylor had identified the applications where his steel could safely revolutionize production: continuous turning operations on large workpieces, heavy roughing cuts where conventional tools failed from heat buildup, and sustained cutting where productivity was limited by the need to stop and cool conventional tools. These represented significant segments of American manufacturing where breakthrough performance was possible without compromising safety. The opportunity for complete vindication came through the 1900 Paris Exposition Universelle. The World's Fair would bring together European metallurgists, American industrialists, and international engineers in a setting where controlled demonstration could reach the global audience that Taylor needed to rebuild. His reputation. The French organizers had allocated space for industrial demonstrations that would showcase the latest manufacturing technologies. Taylor's proposal for the Paris demonstration was deliberately dramatic but carefully controlled. A lathe cutting hardened steel at maximum speed until the tool glowed red-hot, operating under conditions where conventional European tools would fail immediately from heat buildup. The setup would highlight exactly where high-speed steel provided revolutionary advantage while avoiding the interrupted cutting conditions that had caused the August disaster. The demonstration took place on July 23, 1900, before an audience of 200 international observers. European metallurgists from Sheffield, German steel experts from Krupp, French engineers from Schneider, and American industrialists gathered around a precision lathe equipped with Taylor-White cutting tools. The workpiece was hardened steel that represented one of the most challenging applications for any cutting tool. European experts confidently predicted immediate failure when Taylor began the cutting operation at 90 surface feet per minute, 3 times the accepted European maximum. They had calculated that tool failure was inevitable within minutes under such extreme conditions. The mathematics of heat buildup were well established, and no steel composition could withstand the temperatures that such cutting speeds would generate. Instead, the Taylor-White tool cut continuously for 45 minutes while glowing cherry red from cutting heat. The audience watched in stunned silence as metal peeled away in blue-hot spirals, while the cutting edge maintained perfect geometry. European metallurgical theory predicted catastrophic failure, but American experimentation had discovered operating conditions where theory was incomplete. The visual impact was overwhelming. Observers who had dismissed Taylor's work as dangerous American overconfidence were witnessing cutting performance that violated fundamental assumptions about metallurgical limitations. The tool was not merely surviving extreme operating conditions, but thriving under heat stress that should have destroyed any cutting edge. Professor Heinrich von Stauffen from the Royal Institute of Metallurgy demanded to examine the cutting tool during the demonstration. His inspection confirmed that the edge was maintaining its geometry while glowing bright enough to illuminate his face in the darkened exhibition hall. The tungsten carbide structures were performing exactly as White's metallurgical analysis had predicted, strengthening under heat stress rather than weakening. The Paris demonstration established Taylor's vindication before the international audience that mattered most for industrial credibility. European metallurgists could no longer dismiss American high-speed steel as reckless experimentation when they had witnessed its controlled application under conditions where their own tools would fail immediately. The systematic approach that had led to the August disaster had also led to understanding how to apply revolutionary technology safely. Orders for high-speed steel began arriving from European manufacturers within weeks of the Paris demonstration. German machine tool companies wanted to incorporate Taylor white steel into their cutting operations. French locomotive builders sought licenses to use the American heat treatment process. British manufacturers inquired about purchasing steel that could triple their productivity in applications limited by heat buildup. The international response validated Taylor's conviction that systematic American experimentation could surpass European tradition when applied with sufficient rigor and appropriate caution. The August failure had been professionally devastating, but technically valuable, forcing development of operating procedures that ensured safe application of revolutionary capabilities. By December 1901, high-speed steel was transforming manufacturing operations throughout American heavy industry. Baldwin Locomotive Works reported cutting times reduced by 60% on applications where heat had previously limited productivity. Bethlehem Steel's machine shop was operating at capacity levels that would have required additional facilities using conventional technology. Taylor's vindication was complete, but it had taught him the crucial difference between discovery and application. Revolutionary technology required not just breakthrough performance, but systematic understanding of appropriate limitations. The Paris demonstration had proven that American innovation could exceed European capabilities, but only when applied with the same methodical precision that had enabled the discovery itself.